Thank you. Maybe I can explain why we have two screens, because it should be later in the presentation, but the event can happen anytime from now. What you see there, it's a streaming from Versailles about the General Conference of Weight Measures, which is a conference that happens every 4 years. It's the conference related to the Metre Convention. The Metre Convention is a treaty that today nearly every industrialized country has signed, and is in charge of defining the international system of units and somehow maintain it. Today is a particular date because we have the approval of the new international system of units, which is something that I will explain what is. And so this is the formal approval, hopefully. Let's see if it will be really voted. This redefinition passed through a number of technical committees, but this is the real political event where the delegates from all over the world will discuss and hopefully approve this big change in the definition of the units. My talk will explain why this change is necessary. You have enough time to learn about it, because the actual implementation date, so the date from which the new system has to be used, will be in 20 May next year. So there are a few months for the world, the industry, the commerce, and so on, have to implement this new system of units. I will show you that a lot will change from the foundational point of view, very little which will change for the user of the system of units, and so there is nothing to worry about. But it's interesting here in this Politecnico to show that we can enter in some details about what are the new foundations of this forthcoming system of units. So I don't know, it might be now. I don't know, because let's see if we took the right moment. So I can, yes, maybe they are clapping for a different resolution. I don't know. This is the issue. So let's talk about the need for the measurement units. This need is recognized since ancient times. I took some quotations from the Bible. You see that this happens also in all other religious texts. There is the need to have the same weights, have the same measures, or for measure until the 18th century, what is meant is the volume, either the volume of liquids or the volume of solid material, like cereals or whatever, and so it's the mass and volume, actually, weights and the measures. You need to have the right weight, otherwise it's a sin. You must have the right instruments to measure the weights, and you see here two ancient measures of volume, so what was called measure at the time, and you see that the Bible suggests two different volumes, one for liquids and one for solids. And these occurred roughly until the 18th century. Typically, worldwide, there were a huge amount of different units of measurement, and there were different for liquids and for solids. This is the Magna Carta. It's an excerpt. You see that It again explains that you need a single measure and single weights here. And of course, it deals about the most important things, which are wine and beer. And the volume that was fixed by the Magna Carta is the London Quarter, which is 25 liters, so reasonable amount. And this is a foundation of the country, essentially. So the measurement unit enters into the foundation of the country. It is one of the pillars of the foundation of a country. And this happens very often during history. The new king, when expands the domain of a country, impose the measurement units for the whole country in order to maintain control. Of course, this, the number of measurement units explodes with the incoming of the technology and the Industrial Revolution. You see here that close to the beginning of the Industrial Revolution, during the French Revolution, there were these, this is one page of a book containing all the units of measurements at that time that were considered by the French Revolution to be unified. And you see that there are different foot lengths depending on the country, on the city where you are, different measures. This is for cereal of some kind, and so on. Sorry, no, this is for the length of clothing, and so on. So every single thing that you want to buy had its own measurement unit in that particular town. This was the same also in Italy, and it was obviously a mess. And so the French Revolution tried to unify all these kind of measurements, and not only to do this, but also to disconnect the units which were based essentially to the properties, for example, to the arm of the king or to the length of his sword, something strongly related to power, essentially, to the local power. The French Revolution tried to disconnect the units from local and define universal units. And what is common to all humans for all times, hopefully, is the Earth. So the second was defined as a given subdivision of the day, which is easy to measure astronomically. And the meter was defined as 1 over 10 million of the quarter of the meridian from the pole to the equator. And this was a bit difficult to realize, because in order to do that, you need to know the size of the Earth. And there was an expedition of the Lambre machine to go from Dunkirk, here in north of France, to Barcelona, to measure this piece of the meridian, not the whole one, but a sufficiently large piece in order to be accurate on the whole Earth, by triangulation. You see the small triangles, I hope you see them. And these triangles were actually measured by measuring the angle. So for every triangle, you must be inside of the next place. This measurement took, I think, 6 years, and at the end they knew the size of the Earth, and then were able to define the meter, which was then realized with a metal bar, with a platinum bar. Time proceeds. The needs for having measurement units valid worldwide were more and more recognized, and so 20 May 1875, an international treaty was signed, the Metre Convention. This is was the streaming from the conference of the Metre Convention, which is still in valid today. And you can see from the original signatories that Italy was there. And Costantino Negra, the ministry at the time, signed the Metre Convention. You can see here the number of titles that he had written in the Metre Convention. This is the situation today. The signatories of the Metre Convention are essentially worldwide. The red ones are full members. The pink one are associate members. That essentially means that they pay less. And you see that essentially it covers all the industrialized countries. Within the Metre Convention, the international system of units is defined. The system of units dates back, in the present form, dates back from 1960. And you can see here the definition of what are called the based units. There are 7 base units. And for each unit, you have a definition, something that specifies what is the size of the unit. So, for example, the meter is related to the speed of light. It's a given fraction of the length that the light crosses in 1 second. And this is the fraction. So this automatically means that this number is the speed of light in the International System of Units. You can read all the definitions. These are the present definition, valid since 1960. So we have the base units, second, meter, kilogram, ampere, Kelvin, mole, and candela. And you can use these base units to define new units. The new units are actually defined as a product by putting exponents, integer typically, positive or negative, to this product. So, for example, if you want to measure a velocity, you have meter per second, so second to the -1, meter to 1, and all the other exponents to 0. With this product, you can define all the units that you need. Oh, this is the same. There are some units which have special names. The name is just a shorthand. So, for example, if you want to measure power, the power is measured in the International System of Units in meter square, kilogram, second to the -3. And to avoid writing all these all the time, a conventional name was put, which was the watt. And so this is just a shorthand for this notation here. I put the electrical units. I'm an electrical metrologist. You are here in a department strictly related to the electricity, so I will focus my presentation on what changes for the electrical units. But I will talk a bit also about the kilogram in particular. Again, in the system of units, you have the possibility to generate multiples and submultiples, and there are names for the prefixes that you can use to define these multiples and submultiples. So, about the definition. In the present SI, the definition of the units are of very different kind. They are not, let's say, uniform. This is the main reason for the redefinition. Let's read just 3 of them. The kilogram is the unit of mass. It is equal to the mass of the international prototype of kilogram. So the kilogram is this one. It's the piece of platinum iridium, a single object that is kept in a vault in Sèvres, close to Paris, in the Bureau International des Points Mesures, which is one of the organisms of the Metre Convention. And it's there, and it's every time, it's exactly 1 kilogram. It's not something that you have to calibrate. It's a kilogram because it's written in the definition. So very strange, this kind of definition. There are units related to a natural property. For example, the Kelvin is a fraction of the thermodynamic temperature of a triple point of water. So you have a material, you find out the triple point of water of this material, and you can define the Kelvin as a fraction of this thermodynamic temperature. This seems much better in the sense that water is everywhere. There is an issue that the water can change composition because there are isotopes of hydrogen and oxygen. So depending on where you take the water, even if it's ultra pure water, it can have different triple points. So the actual definition here was amended during time, and now it's a definition that relates us to a specific kind of water, Vienna Standard Mean Ocean Water, defined by another treaty. So even this kind of definition, which seems much more universal, water is everywhere, is actually a bit complicated. And this is another kind of definition. The ampere is the constant current which is maintained in two straight parallel conductors of infinite length and zero diameter, would produce a force equal to 2⁻⁷ Newton per meter of length. So you can imagine this experiment, these infinitely long parallel wires. You put an ampere and they attract themselves. So you measure the force of these infinite wires, not obvious in itself, and this defines the ampere. So you see that these definitions, first of all, are very different. Some of them are essentially related to a unique, this kilogram is a unique piece. This ampere is something that seems very difficult to realize, to have in your own laboratory. I must say what is a realization. The realization is the definition of a unit that can be provided by a measurement system, by a material measurer or a reference material. The realization is something that specifies, let's say, the size of the unit. An experiment, like here, if you want to realize the ampere, you need what is called a current balance, ampere balance, we will see. It can be a device. If you want to realize the Kelvin, you need to find the triple point of water, which is done in a triple point of water cell, or it's the artifact itself in the case of the kilogram. So again, very different realizations for the different definitions. It's also possible to have reproductions of the units. A reproduction is something that is not directly related to the definition like the realization, but it's a physical phenomenon that every time you do this physical phenomenon in an experiment, you have the same quantity. So the same, let's say, it's not necessarily the unit 1, but something that can be related to the unit. And I will talk about those later. So let's see what is the definition of the ampere more closely. I put the definition, I already told about it. If the ampere is mechanical, you need to measure a force here to realize the the ampere. It means that all the electrical units are mechanical. If you want to realize an electrical magnetic unit, you need to make, you have to do a mechanical experiment, somehow. We'll see which kind of experiments. There are, in this definition here, embedded inside, there are some consequences that you can find here. There are quantities that are exact. Mu naught, which is the permeability of free space, that nowadays everybody calls, every metrologist, I don't know the others, but every metrologist called the magnetic constant. it's a permeability of free space, is an exact quantity. From this number, you derive this one, which is 4 pi 10 to the minus 7, exactly. Since the speed of light is fixed, also the permittivity of the free space is also a fixed quantity. It's not a nice number, infinite digits, but it's a fixed quantity. And it's, nowadays it's also the electric constant. And what is also constant, exact, is the impedance of free space, Z0, or the admittance, or whatever. This is an experiment to realize the ampere balance. You have a balance, a weight here, and a force made between fixed coils and a movable coil. So you have windings, you put the current into the windings, and the windings create a force, and you can measure the force as a weight. You need to know the gravitational acceleration in that place, which can be done very accurately. And more, you need to know the size of the windings. And this is the very, very difficult things to do, because you have a complex geometry, these windings that go in a spiral, and you need to know exactly what is the position of the winding with an accuracy that is directly related to the accuracy of the realization that you want to do. This balance in the 65 achieved 4 parts in a million. So that means that you have to measure the position of these complex objects with an accuracy of 100 nanometer. So very difficult to achieve. Extremely complex experiment requires incredible terminal stability to avoid changes in the size and so on. Of course, you can compute, once you know the position, you can compute the force with the Ampere law. It is not strictly needed to realize the base units. If you want to, you can realize also the derived units. For example, you can realize the volt. This is an experiment to realize the volt. It's a voltage balance. And you have essentially a capacitor. This is just a guard ring here in orange. The red and the blue electrodes attract together. You measure the force. Put a voltage, I measure the force, and if you know the size of the electrodes, you can find out the relation that relates force to voltage. So you can measure voltage in terms of a force. So a mechanical experiment. This geometry is much easier than the Ampere balance, in the sense that for this is an example parallel plate. You can you can use cylinders or whatever, but it's much, much simpler in geometry. What is the negative part of this, of realizing the volt is the size of this force. This is a voltage balance of PTB, the German Institute. It's a big experiment. These are the electrodes here. And they put 10,000 volts. And the force was just 2 grams between the electrodes, the equivalent of 2 grams of mass. So it's a really delicate experiment. And the force is very small. And you have to scale this voltage from 10,000 volts to 1 volt. So it's a difficult experiment. Took many, many years to develop. This is another realization which is very nice, a very clever idea. The idea is that let's do the same experiment, parallel plate capacitor, but one of the electrodes of the capacitor is mercury. So it's a liquid, conductive liquid. And so when you apply the voltage, the liquid rises. And if you have an interferometer, which is this beam here, you can measure the increase in height due to the voltage. It's a crazy experiment because I don't know if you have ever seen mercury, and everything you do moves the surface. So imagine to construct an interferometer, something that has to reflect the beam exactly in the opposite direction with this thing that if you breathe, if you do anything, it moves. It was made in a cave, something like that. I don't remember the details in the 80s, in order to have a sufficient mechanical stability to make this experiment. Anyway, again, you can think of something else, but it's still a mechanical experiment. Because the present SI define the ampere in mechanical terms, you need to find out the electromagnetic units, you need to do a mechanical experiment. And the mechanical experiments are difficult. A great invention in the 70s was a way to improve the ampere balance, where the forces are more significant than in the voltage balance. It was a great idea by Brian Keeble. So this is called the watt balance, or the Keeble balance nowadays. The principle is this one. You have conductors. This is I'm idealizing the balance by taking a straight conductor here, very simple. You have a current flowing in a magnetic field, which is in this region, the gray one. And there is a force on this conductor. The conductor can move. You equilibrate the force with a weight. This is one part of the story, and this is an ampere balance, exactly the same as before. You have to measure the force. The second part of the experiment is this one. Let's put out the current, just measure a voltage between the extremes of the bar. If I move the bar, there is electromagnetic induction on the bar. And this creates a voltage. So you do an experiment in two parts. First one, you create a force and measure the force. Second part, you create a voltage by moving the bar with a known velocity. The good thing is that if you make the calculations, you don't need to know the field, the magnetic field, because you have two equations. The weighing mode is this one. You can cast the equation to show the dependence on the field which is cut, let's say, by the bar with its movement. And in the moving mode, you can show the voltage, which is again related to the same quantity and the velocity. So if nothing happens, if the experiment is stable between these two phases, you don't need to know the magnetic field, the magnetic field distribution in particular. You don't need to know the geometry, which is the most complicated part in the ampere balance. If you do the calculation, you find out that you have a product of voltage and current, which is related to force and velocity. And so this is a power, and this is the need, why it's called the watt balance. Because it realizes the electrical watt in terms of the mechanical watt. Okay? So again, a mechanical experiment that realizes the electrical watt. This is the experiment that evolved in these years, and it's the one that is used nowadays. This is what it appears really. The straight bar is actually a coil, and you have instruments to measure the position and so the velocity in case of the mass with the interferometry, and you have a system to measure current and to measure voltage. You will see here names, Josephson junction, array, voltage standard, and so on, that I will explain in a moment. So this is just more closely related to the actual geometry. This is the first experiment. This is the coil. This is the balance arm. This is the mass. This is a more recent realization. You see, it's still a big, complicated experiment. This is the American way to realize the experiment. You see that this is 1 meter, so this is a huge experiment. People is here. And of course, Americans wants to do everything bigger. and it has a superconducting magnet to realize the field, and so on. So a very complex experiment. Even the Americans more recently tried to reduce the size of their experiment, and this is the new Watt balance. This is an attempt to even reduce the size, and you see here the weight, the mass that has to be put in the balance, that is spherical instead of the typical cylinder, because it's a silicon sphere. I will show you what's the possibility of using these silicon spheres. Okay, this is too complex. Let's talk about the reproduction of the electrical quantities in the present SI. So you see, if you want to realize the unit, you need to do this very complicated experiment. Actually, there are experiments which are easier to realize, to do, which can reproduce the units. And these are the quantized resistance, the quantized flux counting, and the quantized charge counting, which are the name of the physical effects are quantum Hall effect and Josephson effect, and you can call it a single electron counting. I will talk a bit about this. This is how a device for quantum Hall effect looks like. It's a semiconductor bar. It's gallium arsenide. You have contacts. You put a current flowing through here, and a magnetic field which is perpendicular to this surface. And on these contacts here, if you have the magnetic field, a voltage with the Hall voltage develops. This is the Hall effect. In normal condition, the Hall effect depends on several, on the mobility of the carriers, on the charge carriers themselves, and so on. But if you will go on very special condition, very high magnetic field, very low temperature, look at the red curve. This is the field. This is the resistance. The resistance is simply just the Hall resistance is simply just the Hall voltage divided by the current. It's not a real resistance. It's a ratio between two numbers. You see here that these plateaus occur, fixed values of resistance that in a given range are the same, independent of the field. At the same time, another resistance, which is the so-called longitudinal resistance between two contacts on the same side, goes to 0. So the system seems to be superconducting in one direction and have a fixed resistance in the other direction. If you believe the theory that is behind this, the plateaus are exactly centered on these values divided by an integer. So you have a no resistance, which is this constant, Rk, over I, where I is an integer. You can see that this is the plateau 2, this is plateau 4, and so on. Goes down. And this is the Planck constant over the electron charge squared. So it's a quantized value. Everybody does this experiment, find out exactly the same resistance. There were recent experiment showed that the resistance is the same in two different experiments, 2 parts in 10 to the 12. So extremely, the experimental verification of the fact that this is really exactly the same value every time is increasing in accuracy every year. And so you can do this experiment which is not a mechanical experiment, it's an experiment in quantum electronics, and you can do it with, let's say, 200,000 euros, something. So there are firms that have bought commercial items that realize these, that reproduce this experiment, and so generate a fixed value. Of course, somebody has to tell you what is the value of h over e squared. So you need to know from some other part of the universe what are these values. The good thing is that these values can be related to the fine structure constant with this transformation here. And the fine structure constant is an atomic experiment that can be done with an accuracy of parts in 10 to the 11. So very, very accurate. It's possible to make integrated circuits with this, since it's a semiconductor, so you can do these kind of devices, and this is a device that realizes a different resistance because you have several bars in series and parallel, and it creates 10 kilo ohm, which is a value decadic, very easy to use in everyday using calibration. The frontier now is to use graphene, which is this new material, you know, this layer of carbon on a substrate, a single layer of carbon. And this is a device for quantum Hall effect made in graphene. And the idea, there is the expectation, not yet fully realized, that this quantum Hall effect can be made at much higher temperature and much lower magnetic field than on gallium arsenide devices. And so I have an experiment that can be compact, something that can work continuously with a cryocooler. So an experiment that you can buy and put in your calibration laboratory and leave it running to make the quantized Hall resistance. This is instead an experiment that is much less developed at the moment, is the idea that you can count the electrons. So the idea is based on the fact that if you have a sufficiently small object, if you put an electron, then you need more energy, more voltage to put another electron. Okay? So if you have a given voltage, you can put just one electron on this very small object. You can think of an extremely small sphere, for example. You put an electron, then you put another. To put the second one, you need more voltage. So for a given voltage, you have a quantized charge on the object. Actually, we don't use individual items. What is the thing that confines the charge is a region in a semiconductor or a metal device that is defined by electrodes. So this is an example. This is a semiconducting wire. There are electrodes on top of that. And if you put the right voltage on the electrodes, you define extremely small regions where you can count the electrons. And this is object you can think about a sufficiently complex object. So you put an electron, then you change the potential, you move the electron on the second place and leave it away. And so for every pulse of potential, of applied voltage, radio frequency voltage, you can count an individual electron. And this is an experiment that it works. Doesn't create an ampere, not yet, but you can count 1 billion electrons per second on a single device. And so you can realize something like 100 picoampere, counting charges. The challenge now is to make a lot of these in parallel in order to increase the current sufficiently. This is the third quantum experiment I want to talk about. It's a bit more tricky to understand. Is that you can count single electrons in that devices that I show you. You can count single quantum fluxes. This is done in Josephson junctions, which is this is a thin film realization of a Josephson junction. You have two superconducting metals and a normal metaspacer. The physics is complex. If you put a radio frequency on this device, on the device a DC voltage develops, and this DC voltage is related to the frequency of the radiation, of the radio frequency radiation that you are putting on the device. And the relation between the voltage and the frequency is the Josephson constant, which is again related to the Planck constant and the electron charge. It's a different ratio, but is again Planck constant and electron charge. So you can create an experiment that create the voltage steps. You see here. You see that you have here you have around 40 millivolts. And this step is independent on the DC current that you are putting on the device. So you have a quantized voltage that comes out from the device. The voltage is small, so in order to realize good voltage useful for applications, you need to put a lot of these devices in series and irradiate with the microwave. You can split the pieces, the series, or this long series of junctions, you can split it in binary pieces. And so you can program the chip in order to do the voltage that you prefer. This is a chip that goes up to 1 volt and have 13 bits. It's a digital to analog converter, perfectly quantized, that can go up to 1 volt. So these are devices, again, that you can buy now. This was a thing that we did 10 years ago, and now you can buy. There are companies that give you this kind of devices. Okay, so all this is very nice, and it was nice also in the 90s. And so the people worldwide started to use these quantum experiments, the well-developed one, which are the quantum Hall effect and the Josephson effect, to do their own reproduction of the electrical units in-house. So avoiding doing the complex mechanical experiment, we can just use devices made like integrated circuits. And I said that in reproduction, you need to know what are the constants that you have to put in the experiment. At that time, in 1989, the constants were these values here that you can see. And the experiments were already much better than the uncertainty. This is the uncertainty, the relative uncertainty, 4 parts in 10 to the 7, 2 parts in 10 to the 7. But the experiment you can do, even at that time, you could do 2 different experiments, compare the voltages or the resistances, and you have a good comparison in parts to the 9, parts in 10 to the 10. There is an experiment that is still debated whether it is valid or not, that goes down to 1 part in 10 to the 20. And so these values, for convenience, in order to use, everybody use the same values, were fixed. And these values are called KJ 90, Josephson constant 90, von Klitzing constant 90, because they were defined in 1990. Okay? These units are the ones that we use nowadays. All the electrical units, because from the volt and the ohm, you can, of course, derive the Henry, the Farad, the ampere, the watt, and so on. These are the units that we are using now. So if you calibrate, you ask for a calibration of an instrument, it's not calibrated in SI units, it's calibrated in these conventional units. Since 28 years from, 18 years from now. So, what's wrong? The wrong thing is that the knowledge of the Josephson constant and von Klitzing constant is changed. And now we have more accurate experiments that say that the von Klitzing constant and the Josephson constant are different than before. And the accuracy here you see is much better. A lot of years passed. And so now we have a discrepancy between the electrical units in use, in actual use, and the units that are the SI units. This is the difference. Not big. 1 part in 10 to the 7 for the volt, 2 part in 10 to the 8 for the ohm. So this is one of the main reasons why we need a new SI. One of the main reasons is that the electrical world is moving with a system of units which is not the SI. For practical reasons, because these quantum experiments are better, and we expect that they will improve in the future. For example, the electron counting is a new thing. It's likely that it's possible to be improved in the future. There are new materials, topological insulator, that show quantum Hall effect without a magnetic field. Very low temperature for the moment, very small currents that can be applied. But there is a direction in the future. So it is expected that the electricity world will use more and more these quantum experiments, which are not, in the present system of units, are not related to the SI units. And there is a good discrepancy between the conventional units and the SI units. This is one of the main reasons for asking for a new definition of the units. Okay, no, I will skip this. This is instead the reason that everybody knows that it's related instead to the kilogram. The kilogram is the unit of mass, and the international prototype, which is this small cylinder here, defines the kilogram and realized the kilogram too. It was made in 1889. It was taken out from its vault 4 times, I think. There is one missing here. Anyway, you see very, very rarely, and compared with its copies. And there are a few copies that are exactly in the same place, put on the same condition as the kilogram. They are called témoins. And you see here the difference between the kilogram, which is always 0 by definition, and its témoin. And they seem also to go up. And this creates the suspicion that instead it's a kilogram that is going down, because you can think that they are all the same, all equal pieces. Probably the average is moving less than the individual objects, no? So you can think that the kilogram is moving 35 micrograms over 130 years, not much, again. Why? Nobody knows. No idea. Can we do something about that? Nothing. Because there is nothing that you compare the kilogram by definition with something else. You don't know the absolute change. You simply have a hint that something is ongoing. And this is the main, let's say, the more known reason for the redefinition of the SI. That the kilogram is now inadequate to modern technology needs. You need a unit that can be realized everywhere, not just in a single place every 40 years when you take the prototype outside of its vault. And so this is the main moving idea behind the present redefinition. You see here, this is one of the papers that states this, and is 2005. So many years had passed since the original, let's say, moving towards a new SI. And this is the new SI. So in the new SI, what is done is, let's change the definition of 4 units, the one in red. Let's rephrase all the definitions so they have the same structure. So the blue ones are formal changes. The red ones are substantial changes, okay? So for example, the meter was defined as a given fraction of the length of the path traveled by light in 1 second. Do you remember? Now the meter is the unit for which the speed of light in vacuum is this value. Actually, it's just a formal change. The speed of light is the same as before. These are instead the units that substantially change. Let's take the ampere. The ampere was defined as the force between conductors, blah, blah, blah. Now it's the unit for which the elementary charge of the electron, is this value here. Okay? The Kelvin is defined in terms of the Boltzmann constant. So you fix the value of the Boltzmann constant, and this defines the Kelvin. The Kelvin is not anymore related to the triple point of water. And this is fixed to a value. And this is the most difficult thing to explain. The kilogram is related to the Planck constant. This is very, very complex thing to explain, but the Planck constant is fixed. I can give you a hint, taking this slide here. This is the watt balance, you remember? Electrical power here, mechanical power here. If you measure the voltage with the Josephson experiment and the current with the quantum-Hall experiment, since the Josephson constant and the von Klitzing constant both include the electron charge and the Planck constant, if you do the calculation, you find this expression where there is mechanical power here, the mass essentially, integers, frequencies, and the Planck constant. So if you do a watt balance experiment yesterday, this was a method to measure the Planck constant. When the redefinition will take place, the same experiment will be something to measure mass in terms of the Planck constant. This is the good thing. The experiments are still valid. If you want, I didn't talk about the temperature, but there were a lot of experiments trying to measure the Boltzmann constant. Now the Boltzmann constant will be fixed, and this will be thermometers, something to measure temperature. So no experimental effort is lost in this redefinition. You simply revert the meaning of the experiments. And where these values come from? They come from I don't remember it, I didn't put that. There is a committee for data science and technology, that defines the values, they are called recommended values of all the fundamental constants. Not only this one, all the others, even nuclear constants, everything. And these values are the best that we have in the present system of units. So in the present system of units, many experiments concurred to have knowledge of these values. Now we just cut the uncertainty, put the values into the definition, and from this now, this will be the realization of the units. Okay, what are the consequences from the point of view of electromagnetism, which is the one that I like? Oh, this is just a graphical image to show that you can associate to each unit, you can associate the corresponding symbol of the fundamental constant. These ones were the, let's say, the shorthand definitions. There are also expanded definitions. Let's just read the one of the ampere. The ampere is the SI unit of electric current. It is defined by taking the fixed numerical value of the elementary charge to be this value when expressed in the unit coulomb. Where the unit coulomb come from? Ampere per second, where the second is defined in terms of the cesium clock frequency. Okay? So the definitions are actually consistent, because one of the things that you can find strange is that you define the base units, but there are derived units on the other side. So it doesn't seem perfectly square, but the definitions were made in order to be consistent. You have the detailed definition of all the quantities. What happens in electromagnetism? The electron charge will be exact. So any electron counting experiment will be a realization of the ampere. You don't need any more ampere balances. Since h over e square is also fixed, because h and e square are fixed, the von Klitzing constant is fixed, and the quantum effect is a realization of the Ohm. Same for the Josephson constant will be a realization of the volt. And you can combine Josephson and quantum Hall effect with some slow to have a realization of the ampere. So you see that now you can realize the unit in different ways. You can realize by counting electrons, you can realize it by combining other experiments. This is a sad thing for everybody. The permeability of free space will not be anymore 4 pi in 10 to the 7, which is the only number that I remember easily, and this is a nightmare. Again, also the permittivity will not be the same, and also for the impedance of the free space. The Planck constant will be exact, and so the Keppel balance will be a realization of the kilogram. If you have this Watt balance, you can realize the kilogram. Oh, this is probably, I talked also a bit about these spheres. This is another different route to realize the kilogram. The good thing of the new system of units is that you don't need, let's say, to mimic the definition in the realization of your units. You can use any experiment given that it is connected to the fundamental constants. So if something will be invented in the future, it will, and if new physics even will be found to connect an observation with the fundamental constant, and if there are the right fundamental constants, of course, you can use it to define your units. This is a completely different route to realize the kilogram. The idea is, let's take a sphere, monocrystalline sphere, and it's possible to do monocrystals of this size are commonly used in electronics. You can even have monocrystals height like this. If I count the number of atoms that are in this sphere, and I know the mass of the silicon atoms, I can find the mass of the sphere. This is not done by taking one atom apart, dismantling the sphere. It's taken by taking the volume of the sphere and dividing by the volume of the crystal cell. It needs some experiment. You need an interferometer to measure the diameter of the sphere. You need another kind of interferometer. This is a double interferometer, optical and X-ray, to find out the lattice spacing, the size of the silicon cell. The most difficult part, for which everybody was stuck for about 15 years, is that there is more than one silicon. 28, 29, and 30, unfortunately. And so it was, the experiment was blocked by the fact that it's difficult to define the composition, isotopic composition of silicon. And so they took the hard way. They realized, they made an experiment to create single crystals of 28 silicon. And to separate the isotopes, they went, it was an international cooperation. They went to a firm in the former Soviet Union that did enrichment of uranium. And they asked for, to work in the plant, not for uranium, but for silicon. The plant worked for 1 year to make the amount of silicon that you can find it here. And these plants are huge, are thousands of extremely high-speed centrifuges in series, because you have a centrifuge side high meter working at 50,000 revolutions per second in order to have a slight separation of the gas of uranium in something more enriched in the middle, something more, outside, something more lighted in the inside. And you take this gas, the enriched part, and put it in next centrifuge. And after 5,000 centrifuges, so you have 28 silicon. And so it was an extremely expensive experiment, and now we have these silicon spheres, €1 million each, that you can buy from the German Institute, essentially. And if you have all the other experiments, the diameter and so on, you can realize the kilogram. Just a comment about what are the possibilities that the new International System of Units show. One good thing is that you can, since you just need to connect the unit to the fundamental constant, you don't need necessarily to realize 1 kilogram or 1 ohm or 1 volt. You can realize the unit at the level that you prefer. And this is particularly interesting for mass, because for mass you have to, nowadays, in the present system of units, you have to start from 1 kilogram. What if you want 1 milligram instead, not 1 kilogram? To do this, you must do a scaling. And the scaling is done by putting masses in order to have 1 kilogram and then recombining the masses. And then at some point you go to 100 gram after 2 or 3 days of experiment. And then you go to 10 grams and then to go to 1 gram and so on. And every time you do this scaling, you lose some uncertainty, some accuracy in the experiment. With the new definition, you can realize small masses directly. Small masses down to the microgram. It's a mechanical experiment, but you can do it directly at the value that you prefer. And this can be done for all the units. Oh, these are the values, okay, that you have to remember. This is the paper. This is what happened in the last years. This is a roadmap towards the new system of units. We are here today, General Conference of Weight Measures. This is the promotion, that's me. And this is the implementation day that you have to wait and stay prepared, sorry, we talk about this, for implementing the new SI. So you have a few months to learn all this and change the books, textbooks for physics and so on. Thank you.